Hello everyone, this is Vibhaas Srivastava from TLE Eliminators. Today we're going to be discussing the CP-31 sheet solutions for the 1600 rated problem, Planar Reflections. So let's pull open the CP-31 sheet and let's go to the problem. So it's problem 23 of the CP-31 sheet. And let's go ahead and read it. Okay, so we have Gaurang is grown up in a mystical universe. He is faced by n consecutive 2D planes. Okay, so there are n 2D planes which are one by one after the other consecutive. He shoots a particle of decay age k at the planes. Okay, so he shoots a particle which has some age k at the planes. The particle will pass through the plane directly. However, if every plane produces an identical copy of the particle going in the opposite direction, okay, which goes in the opposite direction, which a decay age of k minus 1. If a particle has decay age equal to 1, it will not produce any copies. Okay, it will not produce any copies. For example, there are two planes and a particle is shot with decay age 3. Then the process is as follows. So let's try to follow along. Right. So there are two planes. So one plane is like this, one plane is like this. And the particle is shot with decay age 3 towards the right. Okay, so decay age is 3 for this particle. And then as it goes through, its age remains 3, right? It will just go through directly. But it will also shoot a particle of 1 minus this decay age. So it's going to shoot a particle of decay age 2 to this side, right? So let's just color them. So the first particle will color green. So we know, like, we're talking about the same particle itself. And then this first reflection will color blue. Fine. And now when it comes through this second, this barrier, then again it's going to shoot a particle with decay age 2, right? Again it's going to shoot a particle with decay age 2. The second screen will shoot it, and then this particle will also go on, right? This particle will also go on. And you know what, let's color this dark blue to not confuse with the other one. Fine, so dark blue. Now as this dark blue particle incidents on the screen, again we get another particle, and this one will have a decay age of 1. Okay, this one will have a decay age of 1, right? So total, how many particles did we have? This decay age of 1 particle will just go on to infinity. It won't produce a copy because it's already equal to 1, so you can't have a copy of 1. That's what they said, right? So total, how many particles were formed? First particle which went through, then this first reflection which was created, then the second reflection which was created, and this final reflection which was created, right? So total 4 particles. As you can see, 4 different colors are there. Total 4 particles were made, right? And that's what it says. The total multiset of particles is d3, d2, d2, d1, right? As you can see here, total 4 particles existed. He's not able to cope up with the complexity of this situation. Let him find the size, help him find the size of the multiset S given n and k. Okay, so he needs to find the size of the multiset. What does the size of the multiset mean? It just means the total number of particles, right? The total number of particles which are produced. Since this size can be quite large, we have to find it with modulo, right? So we just need to take modulo of whatever the size is. Particles go back and forth without colliding. Alright, so particles don't collide, they just go through the planes. Sum of n over all test cases is 1000 and k over all test cases is 1000, right? So that's is already given, right? So we can note down that expected time complexity, right? Expected time complexity. And since sum of n and k is less than or equal to 1000, then our time complexity can be big O of n squared or big O of n times k, big O of n, maybe big O of k squared plus n squared. Anything like this can be our possible time complexities, right? Basically, they should not be like cubed. They can be squared and it'll be fine because it only goes up to 1000. In fact, even a log factor might be fine in this, depending on how you implement it. All right, so let's go ahead and see how we can solve this problem. All right, so we are given a bunch of planes, right? We're given a bunch of planes, right? So we're given a bunch of planes, and we know that the first time the first particle is created is going to go through all of them, right? This is the first particle which is shot, and it's going to be shot towards the right from this direction, that we know, right? And yeah, k is the power of the initial particle and n is the number of screens, right? So this one will have a power of k and it's going to come out over here, right? And this is going to happen. Now every time it hit a screen, there will be a particle of k minus 1, right? Every time it hit a screen, there will be a particle of k minus 1 produced, right? Towards this side, correct? The particle of k minus 1 produced towards this side. Now all of these again k minus 1 particles will again make new particles, right? So when this k minus 1 hits here, it's going to make a k minus 2, right? It's going to make a k minus 2, and again this will happen, right? And this one k minus 1 will go through all the screens and produce k minus 2 here, 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 so on. So there'll be like a ton of particles until the k value becomes 1 and they stop getting generated, right? There'll be a ton of particles until the k value gets to 1 and they will stop getting generated. Okay, so let's try and figure out how we can compute this efficiently, because if we try to keep track of all the particles, obviously the number of particles will become very, very large. We can't just brute force keep track of all particles. Obviously, since we're printing the number modulo, also it should be very obvious that, you know, the number is so large that we're having to take a modulo of it, right? So obviously it's impossible to keep track of all particles initially, right? So how do we approach the problem? Okay, so let's say k is equal to, let's say 3 itself, and there are 2 screens, right? So what happens here is, you can see that there are many repeated computations happening. Okay, so what I mean by that is, let's say I have k equals 3, right? And this particle passes through, then I get one reflection of k equals 2 here, one reflection of k equals 2 here, right? In fact, let there be 3 screens. Okay, let there be 3 screens so we can understand better. This particle form goes through this, okay? And then what happens, all of these k equals 2 go forward like this, and then each of them creates like this k equals 1, right? They're going to create these k equals 1 particles, right? So basically what is happening is, the k equals 3 wale particles, they depend on the k equals 2 particles. The k equals 2 particles kind of create these k equals 1 particles, right? So basically what we can say is that like answer for a k equals 3 particle, okay, k equals 3 particle, what does it do? What does a k equals 3 particle do? It's going to do, like, let's say this is screen 1, okay? So k equals 3 particle hitting screen 1, right? K equals 3 particle hitting the screen 1, hitting screen 1. It's going to basically make 2 things, okay? One, it's going to make a particle which goes left, right? And that particle is not going to hit anything. So it'll be 1 plus number of particles. Let's call it answer. Answer is the number of particles hitting screen 2, okay? Hitting screen 2 with the same k or the same energy, right? So basically it's doing, this particle went to the left, so it just counted as 1. This particle goes to the right, so it'll be hitting the next screen with the same energy, okay? Or let's try to generalize it, okay? So let's say this is some screen, okay? And there are so many screens here and there are so many screens here, okay? Let's say, and our particle is going to hit this screen, okay? The particle has an energy of k and the screen number is I, fine. So what is going to happen is, this particle will pass through and continue, right? So the number of particles generated over here, the total number of particles generated over here is going to be, let's say, let's call this answer of I k, okay? Answer of I k means the answer when a particle of power k is going to hit screen I, fine. This is the particle of power k will hit screen I, and this answer is going to be 2 things, okay? Its answer is going to be, and also from the right, okay, from the right direction, fine. And this answer is going to be hitting the next screen also from the right. So answer of I plus 1 with the same power, because the power does not reduce when you go directly through, towards the right, right? So the number of particles formed by this will be equal to the sum of number of particles formed by this and number of particles formed by this one, okay? So this one will go with k minus 1, right? So when you hit this, one will go with k and one will go with k minus 1. So plus, if k is greater than 1 only, right? So k greater than 1, assume that it is k greater than 1, then answer of I minus 1, k minus 1 towards the left, okay? So towards the left, when a particle is coming from me from the left side, then how many, like these bounces type of things will happen, right? So each particle which goes towards the right, it has this following recurrence relation, right? It has this recurrence relation that the number of particles when you hit screen I with power k going towards right, it will be the same as number of particles if you hit screen I plus 1 with power k while going right, plus when you hit screen I minus 1 with power k minus 1 while going left, right? So we get this recurrence relation for our answer from some simple observations, right? Similarly, for particles going towards the left, like this particle, what will be the answer? So we have this particle, okay, it's going towards the left and it has some power k. What will happen to this particle? Well, it will hit this screen also with power k and it's going to go back with power k minus 1, right? So what we can say is basically for the ones going to the left, we have another recurrence relation, very similar one. We can write it as ans I k left, right? Ans I k left, and this is going to be equal to ans of I minus 1 because it's going towards the left, right? So I minus 1 with the power, same power because it's just going straight. So I minus 1 k left plus k greater than 1. If and only if k is greater than 1, then only it'll create a reflection towards the right side, right? So when it creates a reflection towards the right side, it's going to be answer of I plus 1 k minus 1 because the reflection has one less power and towards the right, okay? So we get two recurrence relation. So this is recurrence relation 1 and recurrence relation number 2, right? And this is the recurrence relation on the answer. The answer we want is going to be hitting the first screen with the power of k. So it's going to be answer of hitting the screen 0 or screen 1 as you want to write it, 0 index or 1 index with the power of k, okay, towards the right because we're hitting the first screen towards the right side, okay? So this is what the answer we want. Also, one more thing, how to change these equations. If there is no screen on left and right, then what will be the recurrence relation, right? If there is no screen towards my right, then this particle will not hit anything, so then this value will become 1, right? This value will become 1. Similarly, if there is no screen on the left, then this value will become 1, right? That's all we need to know. Similarly for this, if there's no screen on the left, it will not hit anything, so the particle will just go on to infinity, so we can say that this will be 1. Similarly, if there's no screen on the right, this will be 1, okay? So that's one thing we need to keep in mind while doing I plus 1, I minus 1, right? So if there's no I minus 1, I plus 1, we just change this whole value to 1 itself. Fine, chalo. What do we need to do next? Yeah, so now we can make the observation that now that we already have the recurrence relations, there is a very interesting observation to be had here, and the observation is basically each value of I, okay, each value of I, it depends on the values of k minus 1, okay? So like I is depending on the value of I plus 1 k and also I minus 1 k minus 1, okay? And in this left one, it's depending on I minus 1 k and I plus 1 k minus 1, right? So what happens is, what we can do is basically, if we already know the values, if we already know and have stored the values for like answer for all the positions for k minus 1, and whether it is left or right, that doesn't matter, we've stored both their values, right? If we have stored already these values, then we can compute the next set of values, right? We can compute the next set of values for answer for all the nodes for k, left, right. Yeah, we can compute these values in O of 1, right, with a DP approach, right? All we need to do is basically go iterate from the correct direction and update the values, right? So here, since I depends on I plus 1, we have to iterate backwards. We have to iterate from right to left, right? So from larger I to smaller I. First we'll calculate larger I, then we can use that to calculate smaller I. So we can iterate from right to left. Here, since larger I needs smaller I to get the answer, what we can do is iterate from left to right. So to calculate this answer, we can just iterate left to right, okay? So we can use this kind of DP approach, left to right, right to left, and calculate and fill all these values in the table, right? So instead of answer, we can just make it a DP array, right? And let us think about what properties of this DP it will have. We just need to use this recurrence relation itself. So this will be the transition. We already know the transition. This is going to be the transition of the DP. This is going to be the final answer, right? So DP of 0 k right. We can make right equals 1 and left equals 0, something like that. So we need DP of k 0 1, right? And what will be the memory of this DP? So the table size for this DP will be big of n times k times 2, right? That will be the memory, n times k times 2, because each screen, the power hitting and the left or right direction, right? So this will be the memory table size or memory complexity. The time complexity will also be big of n times k, right? The time complexity will also be big of n times k, since basically we're going through each screen with each value of k one time, right? Each screen, each value of k will go through one time and will fill the value based on the others. So the time complexity will also be n times k with this approach. Finally, what do we need to take care of? We need to take care of the base case, right? We cannot forget. What all does DP have? DP has base case, DP has transition, final case, and state. Like first state, base case, transition, and the final case, right? So we already discussed the state, base case, transition, all. Now we need to discuss the base case. Okay, the base case will simply be when you're hitting with k equals 1, right? So our DP is working on values of k. So when we're hitting on k equals 1, that will be the DP, right? When our power of hitting is k equals 1. And when our power of hitting is k equals 1, nothing happens. We just have one particle itself, right? One particle itself, and it will just pass through everything. So we can say that DP of every I, right? Every I, k is 1, and left right does not matter. So that's this will be set to 1, right? Because always it will be one particle, no matter which screen you hit, which direction you hit. There will be new particles generated because k equals 1. It does not have enough power to generate new particles. So the answer will always be 1, right? So we're doing DP on the answer, right? So that's about it. What we need to do is we need to iterate from smaller k to larger k. For k, going from 2 to like k, let's call this from j going from 2 to k, right? K is the total number of power. So first we will do the base case, right? Base case, we'll set the base case of DP 1 0/1 is equal to 1, right? So this will be our base case, and then we'll go through each this, and then we're going to do the transition, right? Do transitions, right? According to the formula, and then finally we can return the final answer, which will be hitting screen 0 with the power of k from the right. Okay, so this will be the answer we return. Fine. And as we discussed, the time complexity for this will be n times k. The memory complexity will be n times k. So we can write the time and memory complexity again. Time complexity is n times k, and memory complexity is also n times k. Let's have a look at the code for this. So here's the code. Time and memory complexity n times k. We're defining the mod value. So remember, we need to take mod values while doing the addition. While we're counting the particles, we should take mod, because it will exceed int or long as well, right? So then we take n and k. We define our DP table. Initially the base case is set, so DP of I 0, like k is 0, then all of them will be set to 1. Now what we're doing here, now we're going through all values of j, right? So here it's all 0 indexed, right? It's all 0 indexed. So k equals 1 will be treated as k equals 0. That's why we're going from j equals 1 to j less than k, right? Now we are updating the values for the right, and when we're updating the values for when it hits from the right, what we have to do is we need to update from right to left, right? Because I depends on I plus 1. So that's what we're doing here. We're going to set it to the sum of dp of I minus 1 j minus 1 from the left to plus dp of I plus 1 j from the right. Yeah, dp of I minus 1 j minus 1 from the left, dp of I plus 1 j from the right. So sum of this value 1 plus value 2 percentage mod will be our answer. Right, so that's what we're doing, and we're making sure that if there is no screen to hit on left and right, then the answer will be 1, right? That's why I've written it this way. If there's no screen on the left and there's no screen on the right, then the answer can be 1. That's what we have written. Similarly, same thing to update when you hit from the left side. So when you hit from the left side, yeah, the value will be 1 initially, and then if there's nothing on the left and right, it'll be I minus 1 I plus 1 accordingly, and we update the DP again. We need to update this from I equals 0 to n. So from left to right we need to do the updates. Here from I equals n minus 1 to 0, from right to left we need to do updates. So once this whole DP thing runs, it will fill the DP table, and finally we can just print our output, right? So that's about it. Straightforward DP problem. Just figure out which particles hits which screens. We see that the screens hit are like smaller values of k, so we can just tabulate smaller values of k and get our answer. One last thing to keep in mind is, although this implementation has time complexity n times k, memory complexity n times k, as we see, we only use j and j minus 1, right? And anytime in the table we use j and j minus 1. So instead of having all the k table, we can just have like table of size 2, and we can just swap between them, right? So that is one improvement we can do, and that will improve our memory complexity. So it's called compression of dp, right? So dp compression or something like that, flattening, will improve our memory complexity to O of n, although the time complexity remains the same. And also the memory, even with n times k, definitely fits under the limits, so there's no problem with it. But to do it, in case if you want, you can try it out. Okay, so that's about it for this question. This brings us to the end of this. If you had some trouble understanding this, do practice dp, do rewatch the video and try to do a dry run with these equations, right? And yeah, implement this solution yourself. Try the less memory version as well. Yeah, and yeah, thanks for watching. Hope you learned something, and see you in the next solution. Bye bye.